Thanks very much to the organizers for inviting me to give this talk. It's always a pleasure to talk about imaging a black hole with different audiences. And this is a particularly nice audience to talk to. Already, there's been some very interesting presentations, about black holes of all different masses and kinds. And the one that's going to take our attention today is M87, which is a 6.5 billion solar mass black hole, of course, in Virgo A, 55 million light years away. The results I'm going to present, especially the ones that have to do with the measurements that we made, are on behalf of the EHT collaboration. And the idea behind the EHT is that we set out to make the first image of a black hole, but really it was to create a cosmic laboratory, to turn a black hole like this into a mechanism by which we could look at GR tests, tests of exotic constructs of black holes, but also how jets are launched and how accretion comes to be, and how these black holes are engines of energy and matter redistribution on galactic scales. And I think that in some measure we have succeeded, but there's much, much more to come. So what I want to do in this talk is recap what we've seen, what we've done, give you some of the underpinnings, and then at the end use that to launch a new project that we're thinking of called the Next Generation EHT, and discuss that and let you know some of the things that we're thinking about doing over the coming decade. So you'd be forgiven if you thought this was what black holes looked like. This is a picture that Kip Thorne showed just recently in a wonderful talk he gave. And you can see there are some problems with this, as beautiful as it is. This is a lensed thin disk, which is not the kind of black holes that the Event Horizon Telescope looks at. And also, this is really in the optical. So Kip was telling us that the effective temperature of this disk is about 4,700 Kelvin. So you're really looking at something that's quite impossible. But it does get a couple of things right. Now, one of the things it gets right is the general lensing morphology. So you see the back part of the ring lensed up over the top and also on the bottom. And you see this very thin ring in the center part, and that is the actual photon ring. That's the last orbit of photons around the black hole. And we understand this historically through some work that was started in the 70s by Bardeen and Jean-Pierre Luminet. And you can see that the light from the disk takes different paths to the observer here. And so it's very much of a geometric but light bending construct that gives you this kind of hole in the middle with the looped back part of the disk coming over the top. And on the right part here, you do see that dim region in the middle, which is the shadow, but the shadow here is really defined by the inner edge of the accretion flow of this thin disk, not necessarily by the GR. The small little light band you see here, if you can see my cursor, that is the photon orbit there. That is what is determined by general relativity. The size of that photon orbit is the square root of 27 times the Schwarzschild radius if it's a Schwarzschild black hole, and it's about 9/2 times the Schwarzschild radius if it's maximally spinning. And this is work that's been discussed at length by people like Dimitrios Saltis and Johansson and all the people that you see over here on the left. So a lot of wonderful work being done on the theory here. Now, we can go back 100 years to figure out really what's going on. This is a picture from Max von Laue's monograph, and you can see that the black hole here, which is 2gm over c squared, is the cause of this shadow, but it does not define the shadow. What defines the shadow is the photon orbit, which is out at 3gm over c squared. And the reason for that is if you're off to the right of the screen and you ask what the impact parameter of this black hole is going to be, you realize that it's the light rays that go towards the black hole and then encircle it on that last photon orbit that define that dark region. And that is the square root of 27 times the Schwarzschild radius in the spin 0k. So people knew about this for quite some time going back into the past. Now, this is not really what we see, though. What lights up our space-time for Sagittarius A star and M87 is a low luminosity accretion flow, which is best described by an ADAF, an advection-dominated accretion flow. And you see the spectrum of one on the left. This is really work that was started by Ramesh Narayan and others around 1994. And it describes a two-temperature flow that's flowing onto the black hole. So the ions are much hotter Then the electrons, they advect energy through the event horizon. The electrons do the radiating. And so one of the reasons this can be so low efficiency is that the energy is removed from the system as it passes through the event horizon. These disks tend to be very hot and thick and puffy, which is really nice because they illuminate the space-time from all directions. So you essentially have an isotropic flashlight. And most importantly, this accretion is optically thin, so it is possible to see all the way to the event horizon. If we were in an optically thick part of the spectrum, we would only see the surface of last scattering, and we could never hope to see the strong GR signatures that the Event Horizon Telescope is after. So when you do this and you simulate these ADAFs from a lot of different perspectives with many different parameters, you always tend to see the same structure. It's really defined by the general relativity. So on the left, you see some work by Avery Broderick and Avi Loeb. In the middle by Heino Falke, Melia and Egal, and then Monika Mazobrowska on the right. You always see this circular feature, which is the last inner part of the photon orbit with this dark patch in the middle. You're basically seeing synchrotron emission. Hot relativistic electrons orbiting around magnetic fields is one of the primary ways that these systems radiate. And on all of these, you'll see an asymmetry, and that's due primarily to the light speed rotation of matter around the black hole, Doppler boosting on one side versus the other. So we're after some clear signatures that are really defined by general relativity here. Now, to motivate this, I often show this picture. So you see the optical Hercules A galaxy in the center with these amazing jets that go out for, this spans 1.5 million light years. And then, of course, there's a cooling flow, as you see here in the X-rays. And what's happening here, we think, is there is this ADAF, or this thick kind of donut torus, and it feeds this black hole, and you wind up getting these huge outflows on either side. And one of the main things that we're after in the Event Horizon Telescope, especially for the future, is to make this link between the black hole that's driving these flows and understanding how it creates those flows. What is the jet launch mechanism that gives rise to this? So for M87, we start here in the optical, and we kind of orient ourselves. We zoom in, we see this wonderful optical jet, and it's just jets all the way down. It's like a Russian doll. You see on the upper left here, the VLA at 1.5 gigahertz, this amazingly beautiful one-sided jet, but you know that there are two jets because you have these lobes on either side. So one jet on the right is coming almost directly towards us, very strongly Doppler beam towards us. On the left, you don't see one at all. And then over the course of about a factor of 1,000,000, zooming in by a factor of 1,000,000, you wind up going through this series of self-similar jets, which always approach this core. And then when you zoom into the core, you finally have the resolution and the optical depth sensitivity to see this ring feature. And just to put it in perspective, we love this XKCD comic, which shows just how small we all are. The whole solar system, well beyond the heliopause, it just fits inside that shadow. It's kind of humbling to think about that. So we do this with very long baseline interferometry. I'm assuming most people are pretty familiar with that, although everybody has their own favorite observing mechanism that they specialize in. So we like to disaggregate our collecting area across the face of the Earth. We have different radio telescopes. Chile, where some of our colleagues are today, is one of the primary areas there because they have ALMA and the OPEX telescopes, which work with us. And you record radio waves from the black hole on hydrogen maser. With hydrogen maser clock precision, they lose about 1 second every 10 million years. You record that onto hard disk drives, and they come together in a correlator to be processed. There's so much data, 3.5 petabytes for the experiment that I'll tell you about today, that the only way to get the data back to the correlator really is by loading 747s filled with hard disk drives. There's just no other bandwidth on the planet that you can use. To get data back from the South Pole would have taken us 25 years at the current rate that's possible from that site. And we're targeting really small objects. So the M87 shadow is about 42 micro arc seconds across. the size of an atom held at arm's length, or reading the date on a quarter in New York if you're standing in Los Angeles. And we're observing at 1 millimeter wavelength, which is, I'm just going to tell you, really hard. It's not easy to do VLBI at these short wavelengths. The electronics is noisier. The sensitivity of your dishes goes down because surface roughness on the reflector itself starts to play a role, and the atmosphere, through absorption of precipitable water vapor, can kill you. So we need good weather at all of our sites all the time to do this. Now, this just shows why we need to go to 1 millimeter, not just because of our atmosphere, but because we want to see all the way down to the event horizon. This is some wonderful work done by the University of Arizona, where you see from long wavelengths to short wavelengths, once you get to 1 millimeter, now you can start to see the edge of the event horizon. It's only when you get to 1 millimeter that you can really peer through the hot ADAF structure around the black hole to see these strong light bending signatures. So we got started on this actually some time ago. This has been a long project in its conception and all the way through to the execution. These data were published in 2012, but they were taken in 2009 already, so well over a decade ago. And we launched a first experiment for M87, which combined the telescopes in California, the old Karma array, which doesn't exist anymore. That gives you an idea of how long we've been at this, the submillimeter telescope in Arizona, and then the JCMT in Hawaii. On the short baseline, you expect to get all the flux of M87, which is about a Jansky at these frequencies, and indeed on the left, we do. On the short baselines, baseline is on the x-axis, and correlated flux density is on the y-axis. You see all of the flux density. On the long baselines, we see a dramatically reduced correlated flux, and we're able to get a size from this. And that gave us a full width half max of about 40 microarc seconds. So it was exactly what one would have expected from some of the mass estimates of M87. So we were off and running. And I just cannot help but show this wonderful animation by Craig Walker and his colleagues at the VLBA. They have shown us this animation where you can see very clearly the flow of emission from this unresolved core. So we wanted to zoom in to what was driving this flow that Craig was showing us. So we set out to put a bespoke instrumentation at many sites around the world. And the key thing that I'll come back to at the end of this talk is that we were limited by where these telescopes were. So typically with something like the VLBA or other interferometric arrays, you pick where you want your telescopes to be to optimize the imaging fidelity. And in this case, we couldn't do that. We had to go to these very specialized high altitude sites for 1 millimeter observing. And you can see them all here, the IRAM 30 meter in Spain, 2 telescopes in Chile, Apex Alma, the LMT in Mexico, the submillimeter telescope in Arizona, 2 telescopes in Hawaii, the SMA and JCMT, and of course the hard to get to South Pole telescope at where else? The South Pole. Now, what allows us to do these imaging is the fact that the Earth rotates. So on the left, you see the rotating Earth with all the sites I just showed you, and the red network shows you the connections between all of those sites. And on the right, you can see the Fourier coverage that you wind up getting. Each baseline pair gives you one Fourier component of the image that we're trying to make. So over the course of an evening, you sweep out enough of this Fourier plane, and you see each of these is a Fourier frequency that you can then start to make images. Now, how do we make images? Well, I think it's fair to say that the Event Horizon Telescope project really broke new ground in how we fundamentally image VLBI data. So we are in a sparse sampling regime. So we have 2 terms in our minimization process. We use a regularized maximum likelihood method. So you have a typical chi-squared term, which is the first one on the right. And the second one is also a minimization over some priors. Now, these typically limit where your flux can be in the image. So we don't have a lot of flux on the very, very edges of our image. We like to have it centrally localized. But these are relatively tame priors that we use. We don't seek to find a ring by putting a ring in our priors at all. And as an example of how this works, I'm showing you here a kind of a time lapse of the data being reduced. And you can see it starts to form a ring, and then you'll see it anneal. It'll pop back up and then try to find a new minimum, and always minimizing both the data and the regularizers. And across many different regularizers and with great verification and validation, we're very convinced that when we are seeing a ring, we actually have a ring in truth. Now, we did this partially by having a very rigorous and fun imaging challenge for the first 2 years of our project. So we would create synthetic data, give them to different teams, and they would image them. On the top here, you see 6 different possibilities that were made by our team. And then this was the real image. So pretty good reconstructions there. On this time, there was a little bit more variation in the team results. And of course, you can see here that we were giving them a very much more complex presentation. So over many years, we refined the robustness of these methods. We even gave them things like this. What is this? Is it a jet? Is it, is it an accretion flow? No, it's Frosty the Snowman. You may laugh, but this is actually something that's really important. If you throw something in that people don't expect, you want to make sure that they really are seeing that. And so this was a very important part of the validation process in the EHT. And this was really the brainchild of Katie Bauman, Michael Johnson, Andrew Shale, and Kazu Akiyama. Wonderful early career people who took this on as a cause and pushed it forward, and it was instrumental in our results. Another thing that was really instrumental in our results, and this is partially work that was led by Laura Verticic, one of our postdocs, was the vast increase in bandwidth. So one of the problems in the EHT, or should I say one of the challenges, is that we use preferentially smaller dishes. And that's because at the higher frequencies, they have to be smooth, and it's just difficult to make a large, smooth dish. So they tend to be very high precision, but they also tend to be small aperture, which leads to lower sensitivity. And the real breakthrough, as you'll see on this plot, which shows the year on the x-axis and the recording rate of our very long baseline interferometric instrumentation, goes up exponentially. So we hitched our wagon to Moore's law, and instead of recording on reel-to-reel tape recorders, which we had for many, many years, we made the jump to hard disk systems. We made the jump to fully digital backends, which sample the wide IF from our superconducting receivers and are able to transport them via a stable media back to the correlation facility. And over many years, we've kept pace with Moore's law, and we're now recording at 64 gigabits per second, which is by a factor of about 32 faster than any other VLBI network on the planet. And on the right here, you see the whole system that we developed over the past decade, and this is what's installed in just about every EHT site. So in April 2017, it all came together. We triggered an 8-station array with all the ones that I described to you. We had very, very good weather. We triggered 5 days of weather within about a 9-day period, and we got detections to all of our sites. Now, when we first started looking at the data, since we've been looking at data like this for a long time, we got pretty excited because you can see here that on the plot of visibility amplitude versus baseline, you see this characteristic dip right around a baseline length of 3.5 gigalambda, or billion wavelengths of light, and another one over here around 8 gigalambda. And you ask yourself, well, how can you think about modeling that? And a Gaussian just doesn't fit. A Gaussian on this plot gives you this dashed solid line. Now, if you had a hard edge, a filled disk, then you start to get the ringing that is evident in the data, but it doesn't match the nulls and the peaks of the data. If you carve out a section of this, then you begin to match the different nulls. And then if you create some asymmetry here, you wind up with a family of curves that start to match this. So as soon as we saw this plot, we knew we had something pretty interesting, but we still had to verify that through imaging. And a very important part of the project is, as some of you may know or some of you may not know, is that we set out to tackle human bias. by creating 4 different teams around the globe, each of which looked at the data completely independently. That was a very important part of the process. So we had team 1, 2, 3, and 4, and they were separated partially by geography, also by mechanism. So we had some that were using traditional clean methods of deconvolution to do the imaging, some that were using regularized maximum likelihood, maximum entropy. So everybody came at it differently, but the most important thing was that there was no communication between any of these 4 teams. And when we all came together after a few months of working on the data at the Black Hole Initiative at Harvard University in 2018 summer, this is what we found. We had 4 different teams. Each of them were converging on this ring-like structure. On the right, you see 2 teams that were using more traditional methods, clean, and then on the left were 2 completely distinct but similar in method, regularized maximum likelihood paths to it. And you see the basic structure here, the reduced emission in the middle, indicative of the shadow, and then the asymmetry around showing the effects of light speed rotation around the black hole. Here we are. This is the imaging workshop at which we first described this, and there was also a lot of people on the speakerphone too. So it was a very celebratory moment and a very cohesive one for the project. Now we also looked at other sources just to make sure that, you know, just because we were seeing a ring, we didn't see rings everywhere. And in truth, and these results have also just come out. There could be a whole other talk on these. We imaged the quasar 3C279, and we see the typical core jet structure. This is EHG paper 4, but really this is work that was led by a postdoc, Kim, at the Max Planck Institute for Radio Astronomy. So his name should really be on here as well. Sorry about that. And you see here, you know, extreme bending indicative of very, very high speed flow from the core, which is the northern part, towards the jet, which is the southern part. And there's a whole some lovely results having to do with high speed jets from this source that's now in the literature by the EHT. Now, the other thing about these results is that we had 4 separate days that spanned a week to look at them. So not only is it robust against methods, not only is it robust against other sources, but it's also robust in time, because each of these data sets from April 5th to April 11th was a completely independent data set. And this gives us also great confidence that the structures that we're seeing are very robust. Now, let's talk for a moment about measuring the size of the black hole. There are a number of different ways to do this. You can fit it to general relativistic magnetohydrodynamic models. You can also fit it to images, or you can model it directly. I'm going to show you one of these methods where you basically measure from the image the radius of the brightness distribution around, and you wind up getting a histogram, and you can get to measure the uncertainty of this. Now on the right, you can see that for the Schwarzschild case, when it's not spinning, you would expect the angular shadow diameter, which is what we measure with the very long baseline interferometry, to be equal to, as I showed you before, the square root of 27 times the Schwarzschild radii, 2 gm over c squared, with a d in the numerator because we're of course measuring an angular size, so it depends on the distance to the black hole. So we're essentially making an m over d measurement. And to put it another way, the equation at the very bottom just shows that in terms of the gravitational angular radius, theta sub g. So we have this diameter and uncertainty. We want to measure this theta sub g here. The difficulty is that the ring itself is not directly related to, or is not indicative of the photon orbit. And I'm showing that here. On the top, you'll see a general relativistic magnetohydrodynamic simulation. You can see the ring here, which I'm outlining in the white dotted line. And that really is the photon orbit. And we know that's the photon orbit because this is a simulation, so everything is a priori determined. And if you take that down to the imaged region here, you get a radius. But if you were to fit this actual image And this is an image that's created with synthetic data from the simulation that's on the top. You wind up getting a larger region. So there's simply a bias because you have a lot of emission outside of the photon orbit, much more than you do inside the photon orbit. So we had to figure out what this bias was. Essentially, when we look at a reconstruction of the ring on the sky and we measure the radius of that ring, the true photon ring is going to be smaller. And we're trying to figure out how much smaller. And we did this by looking at about 60,000 GRMHD simulations, and that spanned spin. It spanned the temperature of the electrons versus the temperature of the ions, mad versus sane. Was it a magnetically arrested disk? Was it a standard normal evolution flow? We looked at many different accretion scenarios. And after marginalizing over all of these, we found out what this constant of proportionality was. So at the very top here, you see the angular shadow diameter is some constant of proportionality times that physically meaningful angular gravitational radius. And empirically, we found that that was between around 11.5 with a 10% uncertainty due to the variability in our GRMHT simulations. Now note that in the pure GR case, this would have ranged from 9.6 for a maximally spinning black hole to 10.4 for the Schwarzschild case. So the fact that this is larger just shows you that the fitted ring is a little bit larger than the actual photon ring. Now, so when you do this across all of the imaging methods that we employed, DiffMap, EHT imaging, Smiley, these are all just names for different imaging algorithms that we use. You wind up getting a theta G, which is on the y-axis here, that's remarkably consistent. So on the bottom, you see different days. Each of these bars is a different method. And across all these methods, across all the different days, we wind up getting a pretty consistent angular gravitational radius, about 3.8 micro arc seconds. Now, when we combine that with the distance to M87 of 16.8 megaparsecs with its attendant uncertainties, we can derive a mass now of 6.5 billion solar masses. So, we think this is pretty extraordinary. We're very happy with this. This is the first case we know of where we're using a firm measurement of the photon ring, if GR is correct, to measure the mass of a black hole. And we think this is pretty robust to about the 12% level. So where are we with this? We have this ring diameter that is about 42 micro arc seconds. So we've been able to resolve this. The mass that we derive is, as I showed, 6.5 billion solar masses. It's also circular to within 10%, which is exactly what we expect. If you were to be looking at M87 edge on, you might expect that the shadow would be flattened on one side if it was maximally spinning. We don't see any evidence for that, largely because since we're looking down the spin axis of the black hole, almost exactly about 17 degrees offset from perfect, it should be circular. The deviations we expect from circularity, would be at the 2-3% level. Now, this is all consistent with the prior stellar motion mass estimate. So using stellar dispersion, which is about 6 billion solar masses. So that gives us great confidence that we're on the right track. We do have to note that there is a separate gas dynamics mass estimate, which gives you a factor of 2 smaller mass. There are some reasons to prefer the stellar motion estimate. Stars are better tracers. Gas has certain modeling peculiarities that come from the fact that it can be compressed and has different dynamics. But we do favor the stellar motion mass estimate at this time. Now, it's important to note on this last point that for M87, the consistency with GR is limited by our GR-MHD calibration, really. So, fully this 10%, 11% uncertainty in the mass is really determined by the fact that we had to marginalize over all those simulations. So in the future, when we get better data, and especially with multi-wavelength data, and we can rule out some of these models, hopefully this will get a little bit tighter. So that's something to look forward to in the future for this. But also for Sag star, things should be a little bit better because the distance, of course, is much better known. So we expect our mass estimates and tests of GR to be that much tighter for Sagittarius star than for M87. Now, in some in some contrived cases, you can get the photon orbit depending on the emission itself. Now, this is an important point because when we came out with these results, some people, for example, Gralla, Holtz, and Wald said, well, you haven't really measured the photon orbit. What you've measured is the emission. And they gave some cases, thin disks, or emission that was truncated at various places in a hard way to show that the emission itself could dominate the determination of where the photon ring would show up, or where the shadow would show up. But we've done some fairly exhaustive simulations in response to that. I'm showing you some by Ramesh Narayan, Michael Johnson, and Charles Gamme, who did a masterful job of showing that if you have an optically thin accretion flow, it doesn't really matter what that optically thin accretion flow looks like in detail, as long as it illuminates the space-time isotropically, you wind up getting the same shadow size, which is indicative of the photon orbit, no matter where you put the emission. So on the upper left, the inner part of the accretion flow stops at 2 gravitational radii, and it goes all the way up to 6 gravitational radii, and you still see the shadow that's the same size. So we feel that under most reasonable assumptions, the shadow is truly reflective of the strong GR that holds at the black hole boundary. Now, I want to take a little bit of detour here. This is something that is quite new, that was led by our postdoc Maciek Vilgas at the CFA, and he's asked, what can we learn from historical data sets on M87? So this is the result that we have so far. You can see the forward jet going off to the right. The counter jet ostensibly goes into the page. And then if you wrap your right hand and you point your thumb in the direction of the into the page jet, you'll see that your fingers curl around behind the black hole, come towards you from the bottom, and that's why you see the flow Doppler brightened at the bottom. So we know what the spin axis of this black hole is. We know its basic orientation, and you can see the brightness on the bottom. Now, it's instructive to ask, over time, what do you expect this to look like? So this is a GRMHD simulation over many cycles. And when you blur that, you wind up seeing the brightest part change in angle. And this is just a natural consequence of the turbulent flow. And the gray bar that you see here marks the position of the mean average brightness. And you can see that for a given GRMHD simulation, it can vary. And so the idea was to go back and look at archival data, fitting it now that we knew there was a ring, to find out whether we could see this kinds of variation. And it turns out there was a treasure trove of data from the past, starting at 2009 from the original data that we took on M87, spanning nearly a decade all the way to 2017. And you can see all the sites that were involved on the left here. And what Maciek did was he fit all of these data sets to a model that had a ring and a diminished interior indicative of the shadow. And you can see the results of this here from 2009, 2011, all these different epochs. He was able to constrain roughly where that brightness would be as a function of time. And you can see that it does seem to follow pretty generally some of the different simulations that we've seen. It's too early yet to really make a definitive cut to rule out a lot of these simulations, but we can say a few things based on this really interesting archaeological dig through M87's history. So first on the left here, the model fits that he derives are consistent with this shadow feature from 2009 to 2013, all the way up to 2017. Now that's important because M87 really takes at least a week to vary. So 10 gravitational radii in time is about 3.5 days for M87. And it takes about a week to 3 weeks for matter to orbit this supermassive black hole. The span of historical data that Maciek analyzed with his colleagues is 7,900 M. So we have this almost impossible to get otherwise decade-long lever arm to understand what's happening here. But the shadow does seem to be consistent over long periods of time. And more than that, the diameter seems to be stable. When you fit the models to the historical data, they all wind up being around 40 to 43 microarc seconds. So that's consistent also with this stellar mass estimate for the M87 black hole. So it's powerful evidence that this feature is static. Now, that's important because it could be transient. That's the third point here. You could be looking at an Einstein ring from a bright part of the receding counterjet, for example, lensed around the black hole. We feel that's disfavored, or for a number of different reasons having to do with jet physics, but also time variability in the jet. But having this feature that's fairly stable over nearly a decade really argues against that. Now, in the future, we could use the variability of M87 to start to constrain the models themselves. So on the right, you have what is admittedly a very busy plot. But I just want to call your attention to the fact that this goes through a few different scenarios. So in the blue histogram shows you a magnetically arrested disk accretion flow with half spin and a certain prescription for electron and ion temperature. And you can see in the red many different kinds of models shown. And you see all the different histograms, all the different angular positions of the bright part of the flow as a function of as a function of time through these simulations. And you can see that some are broad and some are narrowly peaked. So the idea here is that over the coming years, we'll be able to use these kinds of histograms to rule out some of the different accretion flows. So I want to move on to the last part of the talk, which is what are we doing next? And we're looking at where to put next sites. And we're looking at many different locations all over the globe to increase our imaging fidelity. I'm going to skip this for now. This is kind of a detail, but basically what we're doing is we're using very strong anchor sources like ALMA or the Large Millimeter Telescope to phase stabilize the array. So we go from what's on the left to what's on the right. The left shows the red phase variations, and on the right you see we can take those out by using the very strong anchor sites. And we use those anchor sites to increase the whole sensitivity of the array. So you see here where the question we asked ourselves is, could we put small dishes anywhere we wanted on the globe and use those anchor sites to get high signal to noise ratio data? And the answer is yes. On the bottom part of this plot here, you see diameter of a small dish. We can go down to a 6 diameter dish and pair it with ALMA, for example. And we wind up getting in 1 second a sensitivity, an RMS sensitivity of about 50 millijanskis. That's incredible. This means we can essentially put a tiny dish at a preferred location and build out the array in a targeted manner to increase our imaging performance. And that's what we're doing right now. We're designing that. It's called the next generation EHT. This is an example. On the left, you see an example array in which we've added about 11 new sites to the EHT array. And you see the Fourier coverage on the right for M87 becomes almost complete out to a certain gigalambda range. And on the right, for Sagittarius A star, which changes on the time scale of a minute, we can make 100-second snapshots of Sagittarius A star. So I want to show you what that looks like. The UV coverage you wind up getting on the left here is extraordinary. In black and gray, you see what we may be able to do in the near future, but in the blue, this is what will happen over the next decade. And this is what you wind up getting when you look at a large field of view simulation on M87. We're going to be able to measure down to a dynamic range of 1,000, we think, the black hole and this jet that's emerging from it. So this is on the left, the real simulation, and on the right is what we feel we can make in terms of a time-lapse movie of M87. So what you can see here is extraordinary, really detailed precision in not only the rotation of the black hole, but in density waves and in the propagation of that jet out to about 400 microarc seconds. And I feel this is actually not as good as we'll be able to do in the future. So stay tuned over the next coming few years. We hope to start to design the array that's going to get us here. Now for Sagittarius star, this next generation concept, we feel that we can make these kinds of images for Sagittarius A star. Here we have to do it in real time because, of course, Sagittarius A star evolves on the time scale of minutes. It takes about half an hour for matter to orbit the Sagittarius star black hole if it's not spinning. So we can't make time-lapse images. We have to make them on the fly. And this is what we think that we can do. On the left is the simulation. In the middle is the blurred simulation. On the right is actual reconstructions from synthetic data that we have engineered from the NGHT. So we think this is absolutely a possibility in the future. And then we want to go to space, of course. On the top, you can see what we do from the Earth. On the bottom, if we had 4 Earth orbiters circling the Earth, we'd fill in the UV plane very, very quickly. And then why stop there? We can go to the second Lagrange point for unprecedented sub-micro arc-second resolution. So we're teaming up with the Origins telescope to see how we might be able to add functionality to their telescope, which is already in the design phase, to make a lever arm that is as long as the distance between the Earth to the L2 point. And if we could do that on the right, we start to get the space-based resolutions on this movie. So we feel this is absolutely possible within the lifetime of an astronomer. I realize I'm over time a little bit. All I'm going to show you here is that the black hole shadow in this central image here really consists of different components. There's an n=0 component where the emission is very lightly lensed around the black hole, an n=1 where it does a U-turn, and then an n=2 where it goes multiple times around the black hole. And the right plot, all you should really take away from that is the big oval, the big red oval shows that we really can't localize the spin or the inclination of Sagittarius star with our current methods, which look at the n=0 ring, this big tufty ring. But with the next generation instrument, we should be able to localize this to this orange ellipse here. So with a real shot potentially at localizing the spin and the inclination of Sagittarius star to within about 10%. And I think this is absolutely possible with the advancement of different algorithms too. And this just shows you the anatomy of the ring. The n=0 is all the emission outside. n=1 is this first inner ring, and by n=2, you're looking at a razor sharp ring here that can really only be resolved once you go to space. There's a huge, wonderful bunch of experiments that can be done just teasing out these rings, which are very reflective, almost uniquely reflective of the GR. And this just shows you how you might do this going out to successive orbits, first a geosynchronous orbit to the moon to L2, and how you see those characteristic rings and beating of the response the farther out you go. I just want to point out too that this is really wonderful work pioneered by Michael Johnson, Alex Lubsaska, and their colleagues. This is an entirely new look on black holes, and it's really been pioneered by some of these early career researchers that have driven it forward. So I'm just going to wind up saying this is us, about 200 members, 60 institutes. It's been a wonderful ride over the past 2 decades. We started small, we've grown immensely, and it really needed a large team to pull off this final stage of the project, and it's been a wonderful experience for everybody. And I'll just leave it here. We've gotten some play in the press, I think it's fair to say, and we always wonder about how to understand this human dimension of our project. Taxi drivers were trying to explain VLBI to me just after the announcement, which was a lot of fun. And I like to think sometimes about how we can take this and help other areas of science like climate change or health, where sometimes public opinion is not as aligned with scientific opinion. So how do we translate black holes into scientific literacy? That's really an open question. Anyway, so thank you very much for your time and attention. Happy to take any questions.